So I can go to my accounts, and there should be a brand new file there. Examples, yep, which was on the 11th, 1233, all looks good. So I can then extract it, like any old zip file. In Linux they just have .tars or .gzs. Extract here, it'll take, it shouldn't take that long really, it's got nothing in it. This must be doing something strange. And now we've got a whole directory full of different files.
Cool. Yep.
So the one we might want to play around with, just for sake, would be hello world, and I'll say hello, you lovely people. How is the weather there? Okay. Just so that there's something different, that we know it's going to be a change. So now that I'm in here, I can obviously run the GCC compiler for this machine, but we care about the one for the processor, okay, the one that we want to fly with ESA. So when ESA write their code, they're going to go to their examples directory. Inside there, they're going to then go to their compiler, run the GCC. Come on, get there. They're going to want to run that hello world.c, and they want to call it ESA's flight code. Yeah, because that's probably what it will actually look like. Steve, Brian, Cliff, not us. So we've now got that file. When I look in my directory again, it's created this file, and it's that size, 112 kilobytes. And so to run it, I've got tsim. TSI, that will auto complete it for me. And when I'm inside tsim, I can either load it directly here by passing it as just a direct file, or I can go in there and I can use the load command. So in tsim, I can type help, and it'll tell me all the things that I can do. So I can watch memories, I can look at status registers, all these sort of things. So there are some interesting ones. What are the ones that status not load? I think I can. They must have got rid of that command. But we might set the debug level. So you can say debug to level 1. You can see it's just debug, set it to a level. Like I said, debug to a level 0. This sort of thing. You're just giving it commands to tell it how to run. And if I wanted to load something, I will use the one that is shockingly called load. And so I've got my ESA program there, so load the ESA flight code, and it will say, yep, we've done that, and it contains a text element and a data element. If you wanted to, you can break those down with other Spark tools to understand what that file is containing and what the assembly actually is. And then to run it, we can see it's loaded in at the start of this address here. So that's about 40 million. So these addresses are virtualized, so in any computer, usually your hard drive will be an actual number, be an address. Your memory, your RAM, will be an actual address. And what they do in operating systems and other sort of systems is they kind of pull them all together, and they'll just go, these addresses from here to here, this is RAM from here to here, it's this tiny little EEPROM here to here, which is your hard drive. 40 million is RAM on this spacecraft. And on this spacecraft we have 32 megabytes of SD-RAM and 4 megabytes of SRAM. Okay, so this thing, I mean, how much does your phone have?
At least 2 gig.
At least 2 gig.
Yeah.
So we're orders of magnitude bigger, better, faster, stronger, all the rest of it. So this is really a tiny kind of processor, and I can type run, and it will run, and it then says hello, little people. How's the weather there? Because that's what we have compiled it to do. I can keep typing run. Once that program is completed. Now if I wanted to, more advanced thing is I can give it an actual address. Run from here. Nope, there's nothing there. Is it there? Yep, there it is. You can actually give it exact addresses to go start code and crunch the assembly from this point here.
From this memory point?
Yep.
Yeah.
Yep. It's very capable what this thing can do.
So you can assign different programs to different memory.
Yep. Absolutely. So this is the sort of utility that you will be doing. Like this is kind of manipulating what computers are doing, when they're doing it, how they're doing it. But that is you building, compiling your program for the LEON3. Been able to run it. But you can see there, it is straightforward. Okay, look at the BCC manual, look at your TSIM manual, because you're going to want to be able to pass arguments into that. So if you're running something that is, for instance, looking at a floating point operation, well, does your hardware actually have that capability? Okay. So of course you can't give it a program that it can't necessarily do. In our directory here, there's a whole bunch of other C files that are doing different things. There's one there called clocktest.c. That may be interesting if you want to ever play with that one. Or there is one called prime.cc, or wheatstone or drystone. There are lots of different files here that do different things that are kind of standard benchmarking type of tools that you would expect to see on software. Drystone, for those of you who remember your DMIPS, that's your guy. So you should be able to, all now, in a very few matter of seconds, cross-compile the drystone for that LEON3, run it on TSIM, and see what result you get. I think that's one of the questions, isn't it, actually?
Yeah, it's based on drystone.
Yeah. I'm telling you what to do, it's all written here. I don't have to say anything. You go ahead and do it.